Welcome to our video on how robot arms know their position. Today, we're going to explore the fascinating world of robot arm positioning and how it's achieved through encoders and feedback systems. When it comes to robots, one of the most fundamental questions is, how does a robot arm know its exact position? Without this knowledge, precise movements would be impossible, making robots far less useful for tasks that require accuracy. The answer lies in devices called encoders. Encoders are sensors that measure the position, velocity, or direction of a robotic joint's movement. They're typically placed at each joint of a robot arm. There are two main types of encoders used in robotics: optical encoders and magnetic encoders. Let's first look at how an optical encoder works. An optical encoder consists of a transparent disc with opaque markings, an LED light source, and a photodetector. As the disc rotates with the joint, the markings interrupt the light beam, creating pulses that are detected by the photodetector. By counting these pulses, the system can track how far the joint has moved. Magnetic encoders, on the other hand, use a magnetic field instead of light. They consist of a magnetic disc and Hall effect sensors. As the disc rotates, changes in the magnetic field are detected by the sensors, allowing the system to track the joint's position. Magnetic encoders are more robust in dusty or oily environments where optical encoders might struggle. Encoders can also be categorized as either absolute or incremental. Absolute encoders provide the exact position at any moment, even after power loss, while incremental encoders only count steps from a reference position, requiring recalibration if power is lost. Now, let's see how encoders fit into the overall feedback system of a robot arm. In a closed-loop control system, the robot controller sends a command to move the joint to a specific position. The joint moves, and the encoder measures the actual position. This measurement is sent back to the controller, which compares the actual position with the desired position. If there's a difference, the controller makes adjustments until the desired position is reached. Many robot arms use what's called PID control, proportional, integral, derivative control, to achieve smooth and accurate movements. The proportional component responds to the current error, the integral component addresses accumulated error over time, and the derivative component predicts future error. Let's see a practical example of how this works. Imagine we want our robot arm to move from position A to position B, rotating 90 degrees. The controller sends the command to move 90 degrees. The joint begins to move, and the encoder continuously measures its position. If after moving for a while, the encoder measures that the joint has only moved 85 degrees, the controller will adjust the motor's power to move the additional 5 degrees. Encoders and feedback systems are critical in many real-world applications. In manufacturing, robot arms need precise positioning to assemble products. In medical robots, precise movements are literally life-saving. And in space exploration, robots need to operate with extreme precision in harsh environments. In conclusion, encoders are the eyes and ears of robot arms, constantly providing feedback on position, which allows for precise control. Without this feedback, robots would be unable to perform the precise tasks we rely on them for in manufacturing, medicine, space exploration, and countless other fields. Thanks for watching.